So, welcome to Renewable Energies. I have a Zoom meeting here running in parallel, and actually 2 students are attending, so to say. Actually, they are so kind to have their camera on, so I have a little bit of the feeling that I have a very small class here. We were just talking a little bit about the date of the exam, and I proposed that we use the Zoom meeting after this lecture. The login data are the same as last week, so they are on Moodle, so that we use the Zoom meeting just a few minutes, so a quarter of an hour or so, in order to discuss a little bit your boundary conditions for the final. Okay, so with this, let me come to what we did. Perhaps a small repetition of what we did last time. So I think I use this one here. So you remember that we calculated that at maximum, so where do I have the figure? Here I have the graph actually. So we calculated that at maximum we can convert about 60% of the kinetic energy of the wind into electricity, say, into work done by the rotor. And the reasoning was quite simple. So the reason was just that we can't stop the wind entirely, otherwise kind of the windmill would be jammed with wind, would be clogged with wind, as ridiculous as it may sound. But this was an easy calculation, and actually this is a very fundamental limit for wind power generation. We then calculated the thrust acting on a windmill, so the force that, would overthrow the windmill. And in order to derive all that, what I just repeated, we used the guess that the wind speed at the rotor is the arithmetic mean between the wind speed far in front of the windmill and far behind of the windmill. Right? And we proved that. This was the Fruit-Rankine theorem. And what also came out was that, of course, we have a pressure difference before and behind the rotor plane. And we found where is this? Here it is. So here's this equation where we have the pressure difference immediately before and after the windmill. And I said, so just because it came to my mind, that would be nice just to calculate how big this is. Well, and I didn't do it so far. What came out from a calculation assuming something like, I think I used 9 meters per second of wind speed, which is a good wind, I would say. And then I would get 50 Pascal of pressure difference. And I thought, well, that's really small, isn't it? I double-checked by just calculating the force according to air drag, to Luftwiderstand. So where the formula is 1/2 CW, then rho, the density of air. What is missing, of course, the area of the wind, so the area that's swept by the rotor blades, and then the velocity squared, most importantly. And of course, now I can divide through A, and I also get the pressure, right? And what you get out is, of course, a similar thing. Well, a little bit more, because this assumes that the wind would be stopped to 0. But so 50 Pascal. So you know that 1 bar of pressure difference would be 100,000 Pascals. So in the weather report you hear you hear typically something like 1000 hectopascal, which is a hectopascal is a millibar. Okay, so this is not much, but actually this is not the full story. You have to think about that the pressure difference is of course only where the blades are. And the blades, they cover only an almost negligible fraction of the area that's swept by the windmill. Yeah? So we have to multiply this number by the ratio of the swept area to the blade area. And this can be almost a factor of 100. And then we would have 5000 Pascal, which is still not very much, right? And from this perspective, I'm a little bit, so I have doubts whether reports that the pressure difference before in the vicinity of the rotor plates, whether this is really enough to kill a bird or a bat, as some people claim. But I don't know it for sure. So if you have better information, let me know. It would be interesting to know. Okay, so we continued to look a little bit not only into drag, Luftwiderstand, but also into lift, Auftrieb. And there we have a very similar formula, just that the area is typically defined in a little bit different way, namely in the area, so that's kind of the depths of the airfoil profile. We'll discuss this soon a little bit in a little bit more detail. So this times, of course, the length of the wing. Okay, so this was one thing, and we said here we have this lift coefficient, and I showed a typical graph on how this looks as a function of the angle of attack, Anströmwinkel, as a function of the Anströmwinkel. And I explained that it increases. It's of course clear that then also the drag increases. So it increases up to a certain point where stall happens, Strömungsabriss. And I gave an example on how important this is, of course, for aircrafts. There I explained that there's only a very small parameter range where such an airplane can actually fly. And we looked at one example, namely the tragedy with Air Force 447, more than 10 years ago. So the lift coefficient is one important quantity here, and it depends, of course, on the design of the profile. The other important, let's discuss a little bit about nomenclature for these profiles. For this, I have a small drawing. So here it is. So this is an air profile, actually a real one, Clark something, one of the famous airfoil profiles. And well, we discussed already what's the angle of attack, right? So what you need is of course a line that defines the profile, which has a volume. So there's probably no unique definition, but actually this dotted line, this is constructed by taking this point. So this is uniquely defined, and then you could say I take the farthest point from this point here, from the trailing edge. So this then would be the leading edge. And then this angle, by definition, or can be defined as the reference line for defining the angle of attack, the Anströmwinkel. And an important quantity for us will be the following, namely the depths of this profile. or as or what the nomenclature is, the chord line. Yeah, so this thing here, and I will call this T. And if you look at a windmill, I brought some with me. Right, so if you look at such a windmill, then you see that, of course, so then you see that the thickness, so this here would be the chord length. So this thickness here, and you see that it's very, very small here at the tip of the blade, and it's fairly large here. Yeah. By the way, this model supports the conspiracy theories that some people have about windmills. Some people claim that there is actually not a generator but a motor here in the nacelle that would just run it for the show. Yeah, for this one it's true. It has here a small photovoltaic cell, so at least it does it renewable in some sense. It has a small photovoltaic cell, but the light here is of course not sufficient. So maybe I replace it by a battery for next time, so that there's more life here. Okay, so and actually what we want to do today is to get an expression for this thing here. Yeah, so we want to calculate this chord length as a function of the radius, and we should get something, as shown here. But before we come to that, I would like to introduce another thing, or perhaps we write that quickly up. So the chord length. Yeah, so this is the depth of the profile of the airfoil. We want to derive an expression for T of R. So that's actually the goal of this lecture today. So, and the other thing that we need is the glide number, the so-called glide number. So what you see, or what you remember, is that we introduced two coefficients, namely the lift coefficient and the drag coefficient, and the glide number is just the ratio between both. Yeah, so the glide number is, I think I call it epsilon actually. Yeah, so the glide number epsilon is the ratio of lift and drag. Because the formulas are the same, it's just the ratio of the respective coefficients. So what we get is epsilon equal Fa to Fw. And and this reduces to the lift coefficient and the drag coefficient. Good. Well, a few examples just for the fun. A few examples for different for different airplanes, let's say. So here. So the first one, which has a huge glide number, which was optimized for glide number. Yeah, so if the glide number is not very large, then you need a lot of energy in order to produce lift, of course. And what you see here is the global flyer, so the Atlantic global flyer, and Steve Fossett, built or designed this, and he flew it non-stop around the world. And yeah, so this was a pioneering thing. Steve Fossett did some other pioneering heroic deeds, and then he finally died in a simple air crash, so in a simple air accident with a small plane that he flew, probably just for yeah, as a hobby or so. Right, so Steve Fossett. Another remarkable airplane is this one here, which made actually history. The US built this thing as a spy airplane, and the interesting thing about this airplane was that it could fly to very high heights already in the 1950s. So what the Americans, what the US wanted to know, what the entire Western world wanted to know, is how far the Russian rocket and nuclear program had developed. And so they flew this so more or less regularly over the Soviet Union at a height of 20,000 meters, such that the Russian air fighters and anti-aircraft missiles could not reach this plane. They realized it at some point that there is something, and actually at some point they shot it down with tremendous effort. They shot 18 missiles at it, and the pilot, this was Gary Powers. Yeah, you see him here. So this picture is from 1966. So they shot him down in the late 50s, and this was a huge thing at that time. So Khrushchev was the Soviet leader at that time, and he was really upset. And yeah, so I think he took off his shoe and slapped it on the table. They sentenced him to 10 years of prison, but then he was exchanged a few years later to Rudolf Abel, which was one of the most important Soviet spies spying on the American nuclear program, and he was sentenced to, I think, 30 years of prison, and they were exchanged in Berlin, actually, on the Klinike Bridge, where many spies were exchanged. And Wolfgang Vogel, who was still around when the Berlin Wall fell, so he organized that exchange or contributed to that. So interesting part of history. So glide number, right? So here you see the glide number. So it is so something like 30 or so. Then we go to the animal kingdom, and here you have a gull, right? So I think herring gull, albatross. It's an albatross. Yeah, so glide number of 20, quite remarkable. If you compare it to the house sparrow, der gewöhnliche Hausspatz, Sperling, which has just a glide number 4, not far from the Concorde when it approaches the airport or so. So you know the supersonic airplane. Okay, so these are a few examples which are typical, and actually these blades are of course optimized for large glide number, and they achieve something like 40 or so. And actually, of course, if you have a glider plane, then they also optimize it for very high glide number, probably even larger than the one that I cited. And they do everything that this glide number is maintained. For example, if they fly through a cloud of insects, then of course quite a few of them get killed at the wings, and some of these air gliders, of these glider planes, they have a mechanism such that they can clean it. So with a hand-driven cleaning device, so that they can clean their profiles in order to increase the glide number. Good. So the other thing that I wanted to mention here, we just cited here this lift, this law for the lift, and actually I put a link on Moodle to an article by Scientific American, which explains, which actually says that nobody really can explain lift. And so there, of course, it's perfectly possible to calculate it by solving, in the extreme case, the Navier-Stokes equations. Yeah, so no question about that, and there are very good approximations for that. But yeah, so a model, so a mechanistic model of lift, nobody can actually. So there's no agreement on a valid one. So quite remarkable after more than 100 years of research or so. But that's not our point. Our point is that we actually want to calculate so we want to calculate the aerodynamic forces at the rotating blades in order to find a condition for the chord line, for the length of the chord line. So we start a new subchapter, namely 6.6. I said already what it is. So we have the aerodynamic forces at rotating blades. Now a few words about the motivation, why we have to do that. So the point is that we have a perfect formula for lift for an airplane airfoil. However, for such a rotating blade, like shown here, the situation is different from an airplane. From an airplane, this foil would just move in a linear way through the air. And therefore, for each point here on the plate, you have the same force element. Here the situation is different because the velocity of the tip of the blades is much higher than the velocity of a blade element, so an infinitesimal piece of the blade and blade element close to the rotor axis. And this is the essential thing that we have to solve. By the way, it has an analog to the propeller of an airplane, and well, actually the physics of the propeller of an airplane was solved before the windmill was looked at, and the ideas are quite similar. And it was Glauert, a British physicist, who derived these laws. But Betz was the one who applied it to the windmills. Okay, so let's write that down. So the conditions at a rotating blade differ from those at a wing, at an airplane wing, at an airplane wing panel, in so far that the velocity of the blade changes like omega, so this is the angular frequency, or the angular speed, I mean. While it is constant for an airplane. Yeah. And actually the point is that the speed of the tip of the windmill, so the speed of the tip of the windmill is typically much larger than the wind speed. Yeah, so this is the dominating speed, and we'll actually introduce a number for that. So the ratio of the speed of the tip versus the speed of the wind. So this is called the tip speed ratio, or the Schnelllauf number in German. Okay, so what we will do is to derive, is to look at the situation with a small drawing. So let me bring it up here. So what you see here is the cross-section through the airfoil, quite obvious, right? Here, the airfoil cross-section, and it moves. So you can think of the rotor axis being in this line here, and of course the wind, the in-streaming wind, is parallel to the rotor axis. So the windmill is always aligned such that this is the case, and this here would be the speed of this element of the rotor blade. Yeah? So what we will do in deriving this length here, the chord length, is that we say we assume that our windmill runs at optimum conditions, so at its design conditions, which means that it runs at a condition where we have a power coefficient that equals the Betz limit. And then, of course, we can immediately say how large V2 is and start a calculation. So let's clarify this. So we analyze the situation where optimum performance is achieved. So where we have the Betz limit, so this means for conditions such that the power coefficient, the coefficient of power, is equal to its maximum, which is the Betz number, right? And we said that this means that the velocity far behind the windmill is 1/3 of the velocity far in front, and that V2 is equal to 2/3 of the incoming velocity. Yeah, so this is this green arrow here. So, if this is the case, then we can calculate by the Pythagorean theorem, we can calculate the in-stream velocity, right? And the in-stream velocity is decisive because it's, of course, this in-stream velocity, which subsequently I will call C, that is responsible for the lift. Yeah? So, again, a small drawing for that, pretty much the same than that I have already, just with the hypotenuse, or something like this here, right? Same drawing, and now this red arrow is the in-stream velocity, and this is so this is decisive. So this is the quantity that goes into the lift formula. So the inflow velocity or in-stream velocity so this means the velocity relevant for the lift force. So the inflow velocity follows from the Pythagorean theorem. So what we have is that c squared, and it depends, of course, on r, because the velocity of the blade element depends on that. So this is 2/3 of v1 squared plus omega times r squared. And just to make it clear, this here is equal to v2, of course. Well, v2 squared to be precise. In addition, we can calculate the angle of the inflow, namely, so this angle alpha here. It's just obviously the tangent. But there's one thing I would like to make you aware of, which is actually apparent from the figure, that this is not equal, so this angle alpha is not equal to the angle of attack that we discussed above. Rather, this here would be this angle here, obviously, right? So you see this dashed line reproduced from before. Yeah. In addition, we find an expression. We find an expression just by inspection of the figure for the angle of the inflow, for the angle alpha of the inflow. So, and what we have is that the tangent of alpha also depends on r, of course, that this is given by v2 divided by omega times r. So let me give these equations house numbers. So that's equation 30, and here we have equation 31. Yeah. Once again, this remark that this is not the angle of attack, it's of course important to know also, to know also this angle here, because this this is the angle under which you should under which you should build in, under which you, this is how you should design. This is also another design parameter for your windmill. And what you see already here is that quite obviously it will be necessary to twist the air profiles independence of the radius, well, just because this angle alpha and therefore also the angle of attack will change due to the fact that the blade is faster closer to the tip. So next we try to give well, a to-scale a graphical representation of the conditions for the wind at these rotor blades. I have this here. So we look at the rotor blades from two different directions. So in this case here, on the left-hand side, we look straight on the plate, on the plane of the rotor, and then here we turn it by 90 degrees. So we look, say, well, at for example, then this here is, so in blue I always have the speed of a blade element, right? And you see that we can easily calculate here, or actually demonstrate geometrically how the speed of the rotor blade, how this increases with the radius. What you also see is here this green point here. So this is the wind that streams head on this rotor blade, right? And you see both things here. So we have here the side view. Yeah, so you see this thing here as this arrow, and this here as this one here, and so on. Yeah? And what you see is that this is, of course, always the same, because the wind that comes from here, the wind doesn't know about the blade. So it's all in the entire rotor plane. It's the same. So this has the same length, but this changes here with radius. Yeah, so you see here, this is really to scale, and in this way you also get an idea on how the inflow velocity c changes as a function of r, and also how its direction changes. Okay, so, and by the way, people call these things here wind triangles. Makes sense. So, quick note for that graph. Perhaps here. So the figure below displays wind conditions at 3 blade elements. From the head-on perspective. So this is on the left. So from the front view, and yeah, and the other is when we look at the rotor, say from above, or from the left, or from the right. Yeah? So on the right, of the figure, we have the perspective from above. Yeah, similar to say this to this figure, where I used my drone in order to get a closer look of the windmill. Actually, what I wanted to see with the drone was whether there are turbulences behind the blades. Right, and we'll see what. So in the next chapter, we'll actually see where turbulences should be. And actually, I saw this a little bit, but I think I would need more experiments, fun experiments. Okay. So next, we define what I already announced, namely the Schnelllaufzahl, or in English, the tip speed ratio. So first point here is a definition. The tip speed ratio. Schnelllaufzahl. Yeah, I think this is a nicer word for what we are defining, and this is called lambda A. I'll come to what the index means. This is the speed of the plate tips. Divided by the wind speed V1 far in front of the turbine. Yeah? And of course what it is omega times R divided by V1. Important definition, because we want to make things kind of dimensionless. So we want to express this chord length as a function of this tip speed ratio. Typical numbers. For a modern windmill, lambda A can be as high as 10. It's not a typical number, but 7 would be a typical number. Yeah, so a typical number is 7. Yeah? And when we speak here of the tip speed ratio, then we mean the tip speed ratio at the design parameters. Yeah, so we assume once again what we said in the beginning, namely that we consider this windmill to be running at the Betz limit. Yeah, so at the conditions for which it is made, yeah, say for for a wind speed of 6 meters per second or for 9 meters per second or so, right? And it's designed such that it reaches at 9 meters per second its optimum performance, right? So this is then the design condition. And this A, this is just the German word for that. Yeah, so the Auslegung, so the design tip speed ratio. So, well, the next thing that we would do is, or what we would immediately do is, to write this equation 31 for later use in terms of the tip speed ratio. I explained that we want to have in the end our formula, yeah, largely independent of the tip speed ratio. So for later use, we write this equation 31 in terms of lambda A. And this is, of course, very easy. The only thing that we need to do is to substitute V2 by 2/3 of V1, and also to substitute, well, this equation 32. So what we had was that the tangent of alpha r, this is now 2/3 times V1 times r divided by lambda A V1 times r, and then we get the tangent of alpha r is equal to 2/3 of r. Well, r is, of course, the radius of the windmill. I hope I have mentioned that at some point. So these are the things so far. Good. Yeah, so just to mention one thing, just a number, a few numbers. Yeah, so we assume a tip speed ratio of 10. Yeah, so for lambda A equals to 10, the inflow direction alpha, we can now calculate, and also how it varies. So the inflow angle alpha varies between 3.8 degrees. Yeah, so this is when r is equal to capital R. Yeah, so roughly 50 degrees close to the rotor axis. Yeah, I think we need a small break, don't we? I have a cup of tea with me, and I hope you also find something in your kitchen. So let's make 5 minutes of a break. You can still see me on Zoom. So let's continue. Next point is that we want to calculate the forces, the infinitesimal forces at an infinitesimal piece of such a plate. Yeah? But before we do that, a few general remarks. The inflow velocity C depends on R, and this means also the lift Fa given by Ca times rho half T times B times C squared. So B, this is the length of this plate element. We'll make a dB, a differential out of it soon. So this means that also the lift and the drag force which is pretty much the same, that they are dependent on R. And this is the reason that we replace B by a blade element, an infinitesimal blade element dr, and we compute accordingly the force elements. And accordingly force by force elements. So what we have is the dFA is given by rho over 2 C squared T times dr times the lift coefficient, and here I write that it depends on alpha A, not alpha, as we discussed several times. And the analogous formula for drag alpha A. And also these equations have a house number 34 and 35. So now let's look how they, how things look. And for this, again, a few, trigonometric considerations, wind triangles in a certain sense. So slightly different perspective here. So you see the rotor axis, of course, and you see the blade moving in this direction, and therefore the wind speed that's due to the velocity of the rotor blade has just the opposite direction. Here we have the in-streaming wind. You also see alpha, and you see the in-stream velocity. So this c that we calculated using Pythagoras. Now the point is that the lift is always perpendicular on the in-stream velocity. So by definition, because the other force that we have, the drag, so this is parallel to it. So you could also say, I decompose the forces that act on such a rotor plate, I decompose it in a component that's perpendicular to the wind speed, this is lift, and to one that's parallel, that's drag. Right? And it is pretty apparent that we can now decompose these vectors here we can decompose them in, well, in directions that are relevant for our windmill. Yeah? So after all, we say that it's the lift that moves the blade, right? So, and the only direction in which we allow the blade to move is this direction here. Yeah? So this is the direction parallel to the rotor plane, right? So this is the interesting part of the lift, and this other part, so this one here is just one part of the force that tries to overthrow the windmill, right? So this is not relevant for the power that's delivered by the windmill. Okay, so what we do next is, so we just write a few words to this for this figure, so that it is clear what is meant. Yeah? By definition, dFA is perpendicular on the inflow velocity, yeah? While dFW, drag, is parallel or anti-parallel. Okay. To C. Yeah? Well, our goal is to find the force that propels the blade. Our goal is to find, well, the force, or rather the component of the force on the blade, that propels the rotor. And we've seen already, this is certainly the component that's parallel to the plane of the rotor. So what we have to do is that we decompose these orange vectors, we decompose them in components that are perpendicular and parallel to the plane of the rotor. So decomposition, so therefore, a decomposition of FA or DFA and FW into components parallel and perpendicular to the rotor plane. Yeah, again, small drawing. So this one here, same drawing than above. The only thing that I did in addition is to decompose these orange vectors. And you see I decompose them as announced in components that are parallel to the rotor plane, shown here in blue, and others that are perpendicular on this, shown in green. Once again, the green ones, they try to overthrow the windmill. And, well, this one here propels the blade, and this one here works against it, as you would guess from drag. Right? So if there would be drag and it would accelerate the blade, then something is fishy, right? So, and you see that this figure represents it in the proper way. So the force components components parallel to the rotor plane accelerate this would be FA or decelerate. This would be FW, the rotor. Yeah, so therefore we look at this one in particular. So we have F parallel equal to F parallel due to drag plus F parallel due to lift. Yeah, and well, you just need to look at the drawing and you immediately find expressions for these components. So one goes like the cosine of alpha, yeah, and this one here goes like the sine of alpha. So what we find is, including sines, all right, so here we have the drag, negative sign, cosine of alpha, plus rho over 2 c squared t times dr, lift coefficient, and then the sine of alpha. And of course it can be written a little bit nicer by factoring out common factors. So we have rho over 2 c squared t dr, and then the lift coefficient times the sine alpha minus drag coefficient times cosine alpha. That's equation 36, and we can do the same thing for the perpendicular component, but this one is not so interesting actually, and therefore I don't really write it down. I just mentioned that it's there. Right? Okay, now we make an approximation. We want to simplify things a little bit, and the approximation we make is actually a little bit questionable, as we will see. So what we say is that we neglect drag, and we say, well, it is justified because the lift coefficient is very high as compared to the drag coefficient, so the glide number is very high. Let's write it down, and then we'll see whether it's justified. But we'll see that it's a little bit borderline. Well, it's kind of justified nevertheless, because there's also a chapter 7 where we will actually include it again. Yeah? So I said it's an ideal, so it's the theory of ideal windmills. And so let's just neglect drag. So so in this chapter we neglect drag, claiming that CA is much larger than CW. Yeah? This means, of course, immediately that DF parallel, that this is approximately DFA times the sinus of alpha, and this is rho over 2 times c squared t times dr CR CA sinus of alpha. So nothing new, right? Just written in this form because we want to plug it in later. Yeah? So, yeah, the question is this approximation a good one? Yeah? Well, sure, CA is much larger than CW. So a glide ratio of 40 is not so seldom. Yeah? So certainly, CA is much larger than CW because glide ratios of epsilon equal to 40 are in fact realistic. Yeah, so for a high performance glider plane, I think they go up to 60 or so. Yeah? But now, if we assume a tip speed ratio of 10, yeah, so is assuming a tip speed ratio of 10, for which we found that alpha is equal to 3.8 degrees at the tip, right? There you see, well, we have a small angle, we have here a small angle, and therefore the lift is actually small. And here, of course, the angle is also small, but the cosine is then close to 1, right? So even that this thing here is much larger than this coefficient, you see that close to the tip, it's not really justified to do that, right? So assuming we found alpha is equal to 3.8 degrees at the tip, and this means that the sign in equation 36 is small, and the cosine also in 36 are close to 1. And this means the approximation is borderline close to the tip, but we could say if we reduce R a little bit, then the angle gets larger. So we set 50 degrees close to the rotor axis. Yeah, so it quickly gets better. Yeah? But as one goes closer to the rotor axis, the approximation improves quickly. And the more important thing is that we will actually quantify the losses due to this issue. Yeah? In addition, in chapter 7, we will quantify the losses due to drag. And the beautiful thing is that you can do this actually analytically. Okay, well, now with these preparations, we come to the decisive chapter, namely the plate geometry according to Betz. Yeah, the so-called Betz design. 6.7 plate geometry according to Betz. The starting point is the following. We want to achieve maximum power. We want to achieve maximum efficiency, I should say. Yeah? So we want to achieve the Betz limit. And if you think about it, this means actually that each ring here has to provide the Betz limit. Yeah? So we need to fulfill the Betz condition for each infinitesimal ring as indicated here. Right? So this is one thing that we, so one requirement, and it will be probably the left-hand side of an equation. And now we calculate, so this power that according to the Betz limit, so we calculate it also in terms of the lift force. And if we say that the power delivered by the lift force equals this Betz limit, this gives us a condition actually for the chord lengths. Yeah. So we have seen that the maximum share of power that can be extracted from wind is 60%, roughly 60% of the wind power. So we have P Betz is 16 over 27 rho over 2 V1 cube r squared times pi. Yeah? So r squared times pi, this is the swept area, of course. So that's equation 40. And now it is only possible to achieve this limit if each infinitesimal ring contributes, well, the respective share. So this power can only be reached if each infinitesimal ring contributes accordingly. Yeah? And we write down what it needs to contribute, namely, so we just need to replace the area by the area of the ring. So this is 16 over 27 rho over 2 V1 cube, and then 2 pi, the circumference, 2 pi r times dr. That's the area corresponding to the green shaded ring that I've drawn. So this is one side of the equation, so this is one side, the right-hand side, the left-hand side of the equation that we want to construct. So the right-hand side. On the other hand, we have power is equal to force times velocity. And in our case, obviously the velocity, obviously the force propelling the blade. In other words, equation, what was it? Equation 38, or if you want to include drag, then it would be 36. So 36, or if we neglect drag, then it's 38. We'll start with the latter. So this means that the force is also given by n times. So n is the number of blades of the turbine. So for this it would be for this one, so you don't see it. For this one here, it would be 3. So I now introduce the number of blades. N times dF parallel, and then the velocity omega times r. That's equation 32. The above one is 42, I wanted to say. So, and now we use equation 38 for dF parallel. So the first point here is for dF parallel, we use equation 38. We neglect drag. And then we get that dP is equal to n times, and now I write the velocity already here, omega times r, and now I substitute dF parallel. So what we have is rho over 2 Ca times C squared, of course, times dr. This is the quantity that we are looking for, times dr times the sinus of alpha. So nothing has happened. I just replace dF parallel with equation 38. Okay, that's equation 43. Another decisive step that I announced repeatedly. So this is the clue of the calculation. We demand that dP Betz is equal to dP that we just calculated. So we demand dP is equal. And if I demand something, then I put an exclamation mark on the equal sign. dP Betz. And obtain by solving and obtain better sentence, and obtain a condition for the chord length TR, well, by solving for dr, of course, yeah? By solving for TR, right? Okay, let's do it. So what we have is N, yeah, so it's 43, I have it on the left-hand side, different from what I just announced. So rho over 2 Ca c squared Tr, this is the quantity that we want to know, dr, and the sinus of alpha. And this should be equal to 16 over 27 rho over 2 V1 cube 2 pi r dr. Right? And as expected, dr cancels, everything else would be strange and an obvious sign for a mistake, but also rho over 2 cancels, and that's it pretty much. Yeah? So we have a fairly complex expression for dr, Tr. So 1 over n, the more plates you have, the thinner one plate can be, makes absolutely sense, right? So 16 over 27, this magic number, 2 pi over times r divided by Ca, and then we have V1 cube divided by c squared omega times r times the sinus of alpha. That's equation 44. Yeah? Now you could say we are done. Kind of. So the decisive things have been done. The only thing that's left is to make this equation a little bit more beautiful by some beauty treatment, massaging the equation such that they get nicer. So this is the next point here. And in order to do that, we look again at these triangles that I showed already, but I just insert them once again. Yeah. So here. Now, so we want to replace, we want to kind of make it dimensionless. Yeah? So we want to get rid of V1 cube and c squared. Yeah? So you see already, so they have some connection. Omega r, sinus of alpha. So let's see. Yeah. So from the figure, or actually figures, we read the following. So we have V1 is equal to 3 over 2 times c times the sinus of alpha. So this you see at the second figure. And what we also see is that U, defined as omega times r, is equal to c times the cosine of alpha. And now if we substitute this into the equation above, then we get, of course, still 1 over n, 16 over 27 also stays, and then we have 2 pi r divided by Ca also stays, but for V3 we substitute the above equation. So we have the cube of that. Yeah? So 3 over 2, the cube of that, this is 27 over 8. Then we have C cube, and then we have sinus to the third power, but I write it as sinus squared times alpha times sinus alpha. Why not? Right? Now, C squared in the denominator remains, but I replace omega r by C times the cosine alpha. Yeah, so I have C times the cosine alpha times the sinus of alpha. And you see that C cube is gone, and you also see that one of the sinus alphas is gone, such that we get 1 over n, 16 over 27. This is actually also 27. Yeah, so this also cancels, and actually 16 and 8. This just we have just a factor of 2 that's remaining. So we have 4 pi r divided by Ca, and then the sinus of alpha times the tangent of alpha. Yeah, so this already looks much nicer, but we are still not happy because alpha also depends on the wind speed and we are not yet done. So from the figure we also read that the sinus of alpha is equal to V2 divided by C, and the tangent of alpha, you remember that we already found an expression for that, so in relation to the tip speed ratio. But here we write V2 divided by U, right? And U is equal to omega times R. Now we use this here together with the always important fact that V2 is equal to 2/3 of V1, and then we find that TR is equal to 2 divided by N, and so I split the 4 in 2 times 2, so we have 2 pi R divided by Ca times 2/3. So this is 2/3 V1 divided by C, and then 2/3 V1 divided by U. And that's equal to 2 pi times R divided by N. This I expand with capital R, and then we have 8 over 9 Ca V1 squared divided by UC. Yeah? Okay, still not beautiful enough. Actually, it's a little bit uglier, I think, but we are not done. Next, we use that U is equal to omega R, and that C squared is equal to V2 squared plus U squared. Okay, I think we should do this, we should finish off with this today. So what we get, 2 pi capital R divided by N times capital R, 8 over 9 and Ca, lift coefficient, And then we have V1 squared divided by omega times r. And now the square root of omega r squared plus 4 over 9 V1 squared. And and now we try to squeeze in the tip speed ratio. So we have 2 pi times r divided by n, 8 over 9 times Ca, and then we have V1 squared divided by omega capital R I forgot here an R, right? Which cancels here. Okay. So then we expand the entire thing with V1. So I always can do this. And then we have still the square root of the entire thing, right? And now if you look at this part here, then you see that this is equal to 1 over the tip speed ratio. So of course 1 V1 cancels, and then we have just V1 over the tip speed, perfect tip speed ratio. Okay, so can do this here, right? So let us continue. So we're almost done. 2 pi capital R divided by capital N, 8 over 9 Ca, and then we have, instead of V1 divided by omega times capital R, we have just the tip speed ratio, and here I have to multiply, so I move this V1 here under the square root, and when I do so, then I get omega times R divided by V1. So you see, I get the tip speed ratio here again, but now squared. I expand with capital R divided by R. And then I have 4 over 9 V1 squared divided by V1 squared. Of course, I could have left that out immediately. So, what we get finally is that TR is equal to 2 pi R times 1 over n times 8 divided by 9 times the lift coefficient, and then tip speed ratio multiplied with the square root of the tip speed ratio squared times R over R squared plus 4 over 9. So that's equation 45. And that's kind of our final result. So the only thing that we could discuss is that if the tip speed ratio is really large, then we can neglect 4 over 9, which is close to 1/2. One remark, final remark. So that would be actually 2 remarks. For fast turbines, the term 4/9 may be neglected. And this means the chord length is inversely proportional to lambda A. So what we would have then is that TR is 2 pi times R, 1/n, 8/9 Ca, and 1 of lambda A squared capital R over capital R. So this would be equation 46. Yeah? And the other remark is that Ca can depend on where you are on the plate. Yeah? So it could be larger or smaller, closer to the plate than the lift coefficient can be different here and here. So, as a final remark, Ca is not necessarily the same for all R. So with this, I'm done. 5 minutes too much. I apologize for that, but I think it's kind of justified because to pick up with these cosmetic changes wouldn't be worthwhile. So it's clear what we do. So I have a few final remarks in this chapter, but then we'll continue with considering also losses. And this will also be an interesting chapter, which, I said it several times that I like this kind of physics, where from very simple considerations you get many things out. Yeah, so I consider this a little gemstone in physics. With this, I thank you for your attention and see you next week.